This is part 2 of my Chapter 2 summary for the Deep Learning book, authored by those on screen. In this video, I'm going to go over the Singular Value Decomposition method for matrices. In the Deep Learning book, the authors provide a short overview of the topic. It was completely new to me, so I did a lot of study with other resources to understand it. As such, this video will attempt to encapsulate all of that. So for full disclosure, in studying to understand the SVD, I quite heavily relied on the work of Steve Brunton, whose YouTube videos did a lot for me to understand the topic. And I recommend you check them out if this overview isn't enough or if you don't understand the ideas that I'm trying to bring across. So getting into it, the SVD has a very, very important use case, which is to make it possible to create an approximation for a given matrix. When I first encountered this, I thought it was strange that it might be necessary to compute the approximation for a matrix, given my background in basic linear algebra and just computing small matrices. But this use case is very important, as matrix approximation can be useful when a matrix is used as a medium for representation of a very large and complex data set. Another really great use case, which is especially applicable in machine learning and ties in with the previous use case, is to use the SVD as a means for variable reduction. That is to say that in a scenario where there are very many variables in a system, the SVD offers a data-driven solution for determining which variables should be focused on and which should be ignored to make a problem small enough to compute while still retaining accuracy. So notably, you'll notice I said data-driven means of variable reduction, and that's to specify that the differentiation and pattern finding in the data comes purely from relationships hiding within the data and not from any human input, such as expert opinion or anything like that. So as it states in the name, the single value decomposition is a form of decomposing a matrix. So you'll recall in eigenvector decomposition, we see that we can decompose a matrix into a set of vectors, eigenvectors, and a set of values associated with them, the eigenvectors. In the surface level sense, the SVD is similar to that, in that we decompose a matrix into a set of vectors and a set of values. But beyond that, it's very different. So in particular, the vectors that we decompose it into come in two distinct groups, the left singular vectors and the right singular vectors, which make up the left singular and right singular matrices, U and V. So when I say the singular vectors, I'm referring to the columns of those two matrices. Following from that, the center matrix, here denoted as D, is a diagonal matrix which contains the singular values. So these are values that are laid out diagonally, and they correspond to the vectors in the neighboring matrices. The first singular value corresponds to the first column in U and the first column in V transpose. So the obvious question is to ask, what are these matrices really? What are the singular vectors and where do they come from? This question is a bit of a doozy, and this led me on somewhat of a wild tangent of learning, which I'll attempt to clarify clearly and intuitively summarize in this video. So firstly, it's important to have a conceptual context. So you can picture the SVD as working on a matrix with some number of columns and then many more rows, so it's a tall, skinny matrix. Then think of each column in the matrix of interest, in this case denoted A, as containing one element of a data set. So again, I'll say I'm very heavily drawing on Brunton's description at this point, but I'll try to make the description my own after setting up the context. So once again, the link to his video is in the description, and huge credit to his chapter on the SVD and videos for helping me to understand it. Alright, so continuing. An element in the data set column of our matrix A can mean, for example, an image of a face. Consider that image as being stretched into a huge list of pixels, making up one of the columns of our matrix. So from a square array of pixels, and just taking each column in that array and laying them out one after another so that our array is now one column, and that's one column of our data matrix A. So that means our data set is a collection of pictures of faces, and each column in A represents one image in that collection. So having our data set on the left-hand side, we'll start off with the most straightforward way of describing what the matrices of the SVD are. But this is to provide a context and the seed of an idea, rather than to try and explain it in a statement. It probably won't make sense for a little while, but we'll unpack it. So U and V, the matrices, contain the eigenvectors of the column-wise and row-wise correlation matrices of A, respectively. Okay, so now that statement out there, we can tease apart and get at what it means. I think it's best to start in reverse within that statement with the correlation matrices. So on the left is matrix A, and on the right is the row-wise correlation matrix resulting from it. Since there are n rows in A, the row-wise correlation matrix is a square with sides of length n. The individual elements of the correlation matrix are the dot products of the row vectors from the corresponding indices. The dot product can be thought of as a Hadamard product of two vectors, so generally it will yield a greater value the greater the value of the constituent elements. That's why this is a correlation matrix. By taking the Hadamard product of all columns or rows to compare them against each other, the column pairings or row pairings, for which both rows or columns have large values, yields the largest scalar, indicating the largest correlations. So returning to the example where each column stores the data for a face, the column-wise correlations store the data for correlation of different faces with each other in their entirety, pairwise. Whereas the row-wise correlation matrix tracks the correlation of the elements of all faces against the other elements in all faces. Put differently, since the image data is in fact pixel data, the column-wise correlation matrix stores the correlation of each ordered set of pixels against every other ordered set, whereas the row-wise correlation matrix compares each set of a given pixel in each image, say pixel number 5000, against every other set of possible pixels from all images. So the set of pixel number 5001, 5002, etc. from all images. So naturally that comparison makes a very large matrix. Okay, so back in the mindset of linear algebra, you might think of this correlation matrix as constituting some transform on a vector multiplied against it. But our premise here is that a vector constitutes a unique face, as encoded in an image. So the row-wise correlation matrix provides a transformation to enact on a face. You might say that the transform encapsulates all the pattern data of how every pixel at every given part of a face usually compares to every other pixel at a given part of a face. So we can imagine it might make the pixels in the shadow of the nose darker than those in the middle of the forehead, for example, and all the other thousands of relationships between points on a face. So keeping that kind of transformation in mind, if you'll recall, an eigenvector is a vector associated with a transformation that when transformed is only stretched by a scalar value, rather than pointing in a different direction. I don't have a video to describe this, but I'll point you to the great algebra visualization series made by 3 Blue 1 Brown, link in the description. It really helped me to understand the concept. So applying that idea of the eigenvector to this scenario, if a vector describing a face, quote unquote, points in a different direction, then we're talking about a different face, insofar as it exists in face vector space. So the correlation matrix could transform a face so that it looked different. Following from this idea, you might think of the eigenvectors of the correlation matrix as representing some faces which, when transformed by that correlation matrix, don't actually look different, because in this really large and multidimensional space, those so-called eigenfaces already match the correlation described by the correlation matrix. So instead of transforming and becoming warped, those are instead made brighter, or in a sense granted more energy, with that energy being quantified by the eigenvalues associated with those vectors. It's important to note that those faces might be totally different from those observed in the dataset matrix. So to pin this down, the notion is that the eigenvectors of the row-wise correlation matrix of the data matrix represent the faces which, rather than being warped by the correlation matrix as a transformation, would instead be brighter, if you take the matrix values to be pixel brightness. So an analog is to think that your transformation gives them energy, with the eigenvalue for each eigenvector being the quantity of energy given. So taking a step back, the matrix on the left contains different constructs of the same form as our data matrix. That is to say, it contains data items which don't necessarily match any items from our data set, but which have an affinity with our data set in that the generated data items exhibit similar correlations within themselves as the stored data items. These pseudo-data items are like building blocks that we can use to reconstruct our data. In the same way that the unit coordinate vectors provide a basis for generating a vector to reach any point on a grid, the pseudo-data we have created provides a basis for adding and blending together these items so as to create a copy of the data item we started with. In the example of faces as data, the notion is that various sets of pixels, each exhibiting some general and/or specific facial features, can be blended together to create an image of a particular face. It should also be noted that since the data matrix A has m columns, thus at most m linearly dependent columns, there can at most be m eigenvectors for its correlation matrices. So at this point, recall that the purpose of the singular value decomposition method is to create approximations for a data matrix and or to perform reduction on the dimensionality of a scenario. So the idea now is that instead of having to store in memory the value of every pixel for every photo of every face, we can instead store a smaller number of faces or face constructs, pseudo-faces, and then store the relatively simple details of how to combine that smaller set of faces so as to recreate our original data set. With that in mind, we need to know how to mix, match, and combine these constructs so as to recreate our original data set. That's where the V matrix and the central singular value matrix come into the equation. So first of all, while our data items may have distinct differences, obviously not everyone's face is exactly the same. There are certain patterns that are broadly applicable to all faces, though. For example, eyes will be slightly recessed, noses reach forward beyond the cheeks, eyes are white around the iris, jaws are U-shaped, etc. As a result of this, there exists a subset of the data constructs, which, regardless of the nuanced variation between the data items, are faces. This subset of constructs plays a significant part in constructing a large number of data items across the data set. These can be identified as having the largest eigenvalues. Okay, so based on this, the working idea is that we can identify and limit ourselves to some number of data constructs, which is less than the total number available. And since some contribute much more than others in building up and replicating our data items, we can limit inclusion of data like those subset, so as to have more gains in data storage compression than we have losses in data fidelity. At this point, I can simply point out that, as mentioned earlier, the central singular value matrix is diagonal, and its contents are actually the square roots of the eigenvalues corresponding to the eigenvectors of the correlation matrices. The reason it's the square root follows from the math, which I'll go into in a later slide. Another point that follows from the math is that the eigenvalues for the column-wise correlation matrix are the same as the eigenvalues for the row-wise correlation matrix. So it's very important to know that since the eigenvalues and vectors are first computed and then used to construct the single value decomposition form, we can organize them within this matrix template as we like. As such, when this format is used, the singular values are ordered in the diagonal center matrix from highest to lowest, and the associated eigenvectors in the left and right singular matrices are ordered to follow that sequence. So, the left singular matrix contains the data constructs, and the center singular matrix contains the singular values. The singular values are sequenced from highest to lowest, with the singular vectors sequenced accordingly in the singular matrix, and both left and right matrix, such that those constructs which generally contribute the most to constructing all data points appear first. Now finally, we can get at what the right singular matrix is for. Stated shortly, this matrix is where the data is stored, which tells us exactly how much each data construct contributes to the blend of constructs that reproduces a given data item. Now let's deconstruct that a bit. As we mentioned earlier, the V matrix is constructed from column-wise correlation matrices. So quick recap, the U matrix was constructed from the row-wise correlation matrix. So it's encapsulated the information regarding the relationship of each pixel of one face to the same pixel in another face for all pairs of faces. So by capturing that information, that matrix provides a sense of what the general components or construction of a face are. In contrast to this, the V matrix results from the column-wise correlation matrix. A column-wise correlation matrix would be capturing the data describing the relationships between all the pairs of faces. So it would give a sense of whether or not one face actually had similarities with another, but without capturing any info about what a face might actually look like. Again, whether or not it's similar to one another is what it would capture. But again, the V matrix isn't a correlation matrix, but rather it's a collection of the most meaningful eigenvectors from that correlation matrix. So similar to how the U matrix was constructed, we might think of the row-wise correlation matrix as applying a transform to the vector, where that vector describes a relationship between one face and a set of faces. And similar to before, the eigenvector of such a transformation is the vector containing the relationship data, which along some dimension is actually aligned with the relationship data stored in the correlation matrix. That alignment is indicated by the eigenvalue. It sounds crazy at first, but those eigenvalues are actually the exact same as the eigenvalues of the eigenvectors we use to construct the U matrix. So that's why the central matrix, that with the singular values, is the way it is. The form all fits together. You have the singular values in the middle, which correspond to the eigenvalues of the eigenvectors on both the right and left sides, even though those are two different collections of vectors. So to close that thought and try and keep this grounded, a given column of V, say the second column, contains the data points which say to what degree that the second data construct, the second column of U, which is like a fictional face drawn from the patterns of all faces, to precisely what degree that particular face contributes to the construction of every one of our original data items. Okay, so for lack of awesome animation software, I've mostly just been talking. So now I'll do a quick overview of the math, which hopefully helps to make sense of the ideas. And again, I highly recommend Professor Brunton's videos, links in the description, for a walkthrough of this that is not in PowerPoint form. So starting off, we'll compute V. As stated before, that's done by taking the column-wise correlation matrix. And that correlation matrix is just a matrix where each cell describes the dot product of the ith and jth elements of A. So we can simply communicate this correlation matrix for A as the transpose of A multiplied by A. Because matrix multiplication multiplies rows by columns, so when you flip A on its side with the transpose, the columns become the rows, and in effect, you're describing a situation where the columns of A are all multiplied by each other. So from the format of the SDV, we can substitute in UDV transpose for A on the right side. The D and U have hats because these are what's called the economy matrices. They are smaller than the original size. They've had data cut off because in the complete form, the D matrix has so many zeros that they reduce lots of multiplication to zero. So you can cut off parts of these matrices and have the exact same final answer. So then on the left side of this term, A transpose becomes VD U transpose. That's because you can compute the transpose by flipping around the sequence of the things you multiply to get A, in this case UDV transpose, and taking the transpose for each of them. So V already had the transpose applied to it, so that just became V without transpose, and D is a diagonal matrix, so taking the transpose doesn't change it. As a result, in the center you have U transpose multiplied by U, and since U is orthonormal, this creates the identity matrix, which is like multiplying by 1 in matrix computation. So that reduces, and altogether it simplifies to V D squared V transpose. And as you may recall from the last video, that matches the general form for an eigenvector decomposition. So from there we can construct this expression for the eigenvectors of the correlation matrix as being described by the matrix V, and the eigenvalues being stored in D squared. At this point, I hope I'm sounding like a broken record, but you can follow through the same math process to find that doing this for the row-wise correlation matrix yields the same outcome, except with U instead of V. And that's why V and U have the same eigenvalues. So as per the usual, when it comes to eigenvectors and values, in this format we can rearrange them to be from highest to lowest, and that's why our SVD can take on such a meaningful form, with the most significant data structures in sequence. It's because we can reorder them after computing them. So hopefully just seeing the math helps to make it a little bit more intuitive that these two sets of eigenvectors would have the same eigenvalues. And you can think about it this way as well. Our conjecture with the SVD is that you can construct some data out of representative building blocks, and that some of these are more representative than others. Let's continue with the example of faces. So, if our pattern recognition here has pulled a so-called average face from a data set, and it's our first building block, it's the first column of matrix U. Since we're defining it as being the first item in U, we're saying that this face is the most average face in our data set. It has the highest eigenvalue. Given that, wouldn't it only make sense that the same face would be used in the greatest proportion to all of the faces to reconstruct our data? Wouldn't it make sense that the most average face has the most correlation to every face in the dataset? Hopefully this train of thought provides an intuitive reason for why the eigenvectors collected in U and those in V have matching eigenvalues. So I'll end this video with the evaluation of the math, which I think will wrap up and put a bow on everything that's been said so far. So what's on the screen right now is what the SVD looks like, so we can break it down. So again, we're multiplying the economy matrices. The whole objective of the SVD was to create an approximation. In other words, to reduce the dimensionality of our data. That is to say, to reduce our count of how many different measures define our data. So we've cut off our U matrix at column M. So we've reduced our set of building blocks, where we've thrown away those of them that didn't have much applicability, that weren't used much. We're losing some fidelity. So our outcome will be a model for building the data set by using M different building blocks, thus M unique dimensions, where before we had many more, because we were thinking about data items as a unique collection of pixels, as opposed to a patterned set of items. So when there are three matrices being multiplied, it doesn't matter whether or not the first and second are evaluated first, or the second and third, and then the first. So for the sake of making more intuitive sense, we can start with the first two. So taking these two, it's really simple to multiply, since there are so many zeros in the diagonal matrix. So the matrix multiplication is computed as row by column, right? So in the first column of our singular matrix, since every element except the first is 0, the result is that the first column of our output is simply the first data structure, the first building block we have, the first face, the most average face from our data, multiplied by a scalar factor. So you can think of the singular value as providing this particular face with a boost, like a signal boost, given that if you had to choose one building block to represent all your data, this would be the best one. Although it would still be a bad approximation because you're only using one building block. So given the nature of multiplication with a diagonal matrix, this pattern continues. The result of this multiplication is a matrix containing all the same faces as were encapsulated in U, but now with each boosted according to its importance in representing the data set, such that if you smeared all these together, it wouldn't be a complete mess. The boosted faces would push the total smeared, kind of blurred, joined up face closer to something with what might be a recognizable average facial structure. So once you've multiplied those two, then you multiply that by V transpose in accordance with the SDV form. So as we've said earlier, these columns can be thought of as storing a vector describing the relationship between each data structure we had in U and each data item we originally started with. In accordance with the strategy we've been discussing about using the building blocks to make up our data items, naturally we're going to use a mix of our building blocks and blend them together to make a given data item. So that's why we're using the transpose of V. It makes sense here. It follows from the multiplication that for every element of every data item in our original data matrix A, that item is the result of aggregating different amounts of each building block, of summing the building blocks that contribute towards it. So you can think of this as, you can think of the V matrix containing like the recipe for each data item, where the different faces, the different data constructs are the ingredients. So data item 1, face 1, might be 20% of data construct 1, 5% of data construct 2, 7% of data construct 3, etc. And it's this whole list of the degree to which each construct, each building block, contributes to a given outcome. So this is basically the end of my presentation. I hope that this mathematical presentation really brings to light the metaphor I've been trying to illuminate this whole time. To say it again, the SVD method breaks down a matrix by identification of pseudo data vectors, which are abstractly representative of the stored data. Then, by identifying the relationships between data vectors, the method offers a means of constructing a data set from a basis derived from that set, but which is not necessarily a distinct part of that set. In the form of an example where the data matrix stores faces in columns, the U matrix column vectors can be thought of as storing pseudo faces which capture typical patterns in the dataset. These are ordered from left to right in the order of the pseudo faces that capture the most prominent and typical patterns to pseudo faces that capture less common or distinct patterns. To complement this, the singular value matrix in the middle stores the singular values for each of those pseudo faces. Those values, in proportion to one another, indicate how much more prevalent a given pseudoface is within the dataset, which relates to how much weight a given face will have in being applied to construct elements from the original dataset. Lastly, the V-matrix column vectors then store the unique weights, which are to be assigned to each pseudoface for each data point to be constructed. So by boosting each pseudoface with its associated singular value, and then multiplying each by its associated weight factor, and putting together the results, the SVD method offers a way to approximate the data. It can be used to compress data, since less of it is retained at some loss of data fidelity. Or alternatively, the constructed set of pseudofaces can be used to attempt to construct new faces which weren't originally present in the dataset. Additionally, the unique combination of pseudofaces and the weights assigned to mix them in attempting to emulate a given person's face can be used as a kind of digital signature for the purpose of facial recognition, for example. So that's what we can see on the bottom here, the mathematical expression for the summations of face element, building block element multiplied by its boost signal boost factor, singular value, multiplied by its weight for a given data item. So once again, this video series is attempting to become proficient in the subject matter of deep learning book, but this video has drawn tremendously heavily on work by Professor Steve Brunton at University of Washington, so I'm grateful for the resources he's made available online, and links to those in the description. I recommend checking them out if this video leaves any confusion on the topic. Thanks for watching, and I hope that this has provided some basis for understanding the singular value decomposition method. Take care.